Hi, I'm Will. I'm going to be giving you a talk on Alan Turing's leopard spots. Now, some of you might be thinking, what does this have to do with the overall theme of refactoring? Well, if you're paying attention, at some point during the talk, I'll give a clue or a hint, and yeah, you'll know exactly what's going on. Alan Turing's leopard spots. Question: what do leopards, zebras, pufferfish, and Alan Turing have in common? They all have. Oh, yeah, go ahead.
They're trying to disguise who they really were.
Yeah, that is one. It's not what I got on the card. Sorry, you've lost the car. Yeah, go ahead.
They all have more hair than I do.
That is very true. I don't know if pufferfish have hair, but there we go. Pufferfish hair. Where was I? Oh, what do they all have in common? The actual punchline is a lot less funny than both of those. They all have distinctive spots and stripes, except for Alan Turing, who's just a famous computer scientist. Oh, God. OK, I've massively misjudged the whole thing. OK, so Turing was a man of many talents. He invented Turing machines when he was working on his thesis, the Church-Turing thesis, with his PhD supervisor, Alonzo Church. So that's pretty impressive. He invented computers. That's why we're all here now. God knows what we'd be doing otherwise. He also invented the Turing test, so arguably is the founding father of AI. And also he cracked the Enigma code while working at Bletchley Park. So he basically beat the Nazis during World War II. So that was in the 30s he invented computers, in the 40s he beat Hitler. So by the end of the 40s he's had a fairly storied career at this point. And he was getting a bit bored, so he thought, he was about 39, he thought, well, what am I interested in? Well, he became interested, near the end of his life, in life itself, okay? He was very interested in how life can go from a single cell, single homogeneous little cell, subdividing and reproducing, how it can then turn into one of these fantastical forms of, like we see before us today. How can a single cell turn into a cute puppy, or a dolphin, or a zebra, or anything you can imagine? And yeah, he was fascinated by this. And at the time, there was DNA hadn't been discovered or extracted yet. That happened in the 60s. They knew about genetics, so he was familiar with the way biology potentially worked, but it was still kind of a mystery. So in 1952, when he was 39, he published an important paper on biology called The Chemical Basis of Morphogenesis, which sounds quite wordy, but it's actually pretty straightforward. Morph, shape, genesis, the beginning, so it's the beginning of shapes from chemicals. And yeah, in doing so, arguably, he founded the discipline of computational biology, so kind of rounded out the start of the decade. Can't round out the start of the decade, but that's fine. So yeah, the chemical basis of morphogenesis. He postulated that there's a hypothetical set of interacting chemicals that he calls morphogens, that as long as they follow a certain set of rules, very, very simple mathematical rules, could, hypothetically, generate all the interesting, intricate, complex fractal patterns that we see on, for example, a zebra's hide, or a leopard's skin, or a pufferfish, or all the different things, even plants, it can work for anything. He was very candid about the fact that he was thinking in very simplified terms, and actually, in real biology, it's a lot messier. It's more than just two chemicals in biology, if you can imagine such a thing. So yeah, he thought he could explain stripes, random spots, intricate coral-like patterns. It could explain the transformation from blastula to gastrula, right, which is when a cell kind of inverts and forms kind of a concave-type structure. And these morphogens, he imagined, were simulated using a process called reaction diffusion. Now, I don't know if he invented reaction diffusion or if it was an idea beforehand, but the paper just mentions it. So reaction diffusion, imagine a 2D grid, okay? You've got a series of cells, and each one of these cells has a certain chemical concentration. Let's imagine that red is chemical A and blue is chemical B, okay? At any given point, when we want to find out what happens next in our reactive diffusive system, we simulate, first of all, reaction. So for any given cell, it detects, let's say I'm this blue cell here. I have some red chemical near me, so I take some red chemical, I take my blue chemical, and I put back 2 units of blue chemical. Okay, so the chemical A is feeding into chemical B. And then you diffuse the chemicals. So you essentially just average each cell out with its neighbors, okay? And it's that simple. And from that, he argued that interesting things can happen. He called the diffusion step is often called a convolution, and it's how a lot of things like Photoshop works. Okay, if you've used a Photoshop blur or a motion blur or any kind of image filtering technique, for example, edge detection, sharpening, they're all based around this idea of convolutions. So what is a convolution? Looks complicated, don't panic. A convolution is just, doesn't have to be a 3x3 grid, but in the simplest case, it is. A 3x3 grid of numbers. We're going from 0 to 1 here, but you could use larger numbers if you wanted to. These are known as your weights. And then you have your input data, okay? And your input data, these might be pixels in an image, for example. This could be your face, and you're wanting to, I don't know, sharpen your face. In this case, we're actually going to be doing an averaging effect. So this is a Gaussian blur. And the way it works is every single pixel or input cell lines up with its weight. They're multiplied together, and that gives you the final answer. I've already done this, so I mean, please do check my maths if any of you are good at maths. But for example, it would be 0.7 times 0.05, 0.68 times 0.2, so on for all the rows. The middle here, 0.29 multiplied by -1, which seems kind of confusing. But the idea is that the cardinal directions, you each get 0.2, so if you add those up, that's 4, 6, 8. Add up the ordinal directions, diagonal directions, you get, well, that's the remainder. So now that's adding up to 1. But then you take the center cell and you multiply that by -1, so it averages out. Instead of adding, it dissipates. And it's that simple. You can have other weights that have different behaviors. So for example, edge detection would have some positive numbers along here, some higher numbers, and then they would be inverted along the top. All sorts of things you can do. So as an aside, one of the breakthroughs behind the recent AI bubble or fad or fantastic investment opportunity is that, as some people might call it, is the I don't want to say discovery, but rather efficient implementation or the ability to implement something called a convolutional neural network. Now, a convolutional neural network is essentially based on the idea of these convolutions. So in the past, in the 70s and 80s, they imagined that all neural networks would just have fully connected layers, maybe say 5 or 10 layers, where all the neurons are connected and it kind of learns and does all that kind of thing. The problem with that is to get anything useful, you need huge numbers of layers. I'm massively simplifying. If anyone here is interested in AI, they're probably twitching. Just calm down, it's fine. It's not accurate, but it works for the analogy. If you put some convolutional matrices in front, then you can dramatically reduce the number of layers you need, because here's a concrete example. Let's say you're trying to recognize a cute puppy in a field. Okay, there is information about in that photo, for example, that the puppy's in the top right of the photo. It's actually not relevant to it being a puppy. It doesn't matter where it's in the photo, it's still a puppy. So by averaging out that information using a convolutional matrix like this, you essentially remove that information. And then, if you want to detect it's got cute floppy ears, well, you could have a convolutional matrix with the weights designed to detect the lovely shape, the undulating shape of its little ears. The crucial innovation with convolutional neural networks is that the weights themselves are not hard-coded. So we're hard-coding them here, but convolutional neural networks learn their weights. So they learn automatically what to average out, what to detect. It really was only made possible by the advent of highly programmable and fast, powerful consumer graphics cards. Because if you're doing 3D games, you're doing lots of matrix multiplications, lots of multiplying of numbers, turns out you can use them for doing convolutions. Moving on. That's not the button I meant to press. Okay. So this is all very difficult to visualize. We've heard some vague terms, but what does it actually mean? What would it actually look like if you imagine this set of chemicals? Well, luckily, in Turing's original paper, he actually sketched out what this might look like. These Turing patterns. So this is Turing's own handiwork. It actually took him a few hours to compute this because he wasn't using a computer in 1952. He's doing it all by hand, and it took him, let's say, an evening or two. And yeah, according to his rules, remember that you've got these grid of chemicals that are reacting and diffusing. He imagined it would look something like this. But nowadays, we have computers, so let's do it properly. This is an approximation of what I think he was trying to simulate. The paper, the way the parameters and the formulas are arranged, it makes it quite hard to transcribe directly into code. So this is my interpretation. Hopefully it's accurate. Let's see what happens. Let's see if it loads, because it might not. So this is being simulated. This is a recording, but it's being simulated on a computer, as you can imagine. So it's kind of vaguely what he drew, right? Does that make sense? It's kind of roughly analogous. It's hard to recreate exactly. Here's an alternative, which is pretty similar. Well, it's a very different way of doing it, but comes out with the same kind of image that he showed. This one doesn't compress as well. So you can see that his still frame that he sketched out hypothetically could have been a still from this. How exciting. Yeah, let's get pumped up. Turing patterns. It's like something from the 60s, but 10 years before. This is what a typical Turing pattern would look like using some pretty straightforward rules. The other ones I showed you were a bit more adventurous. So this is a single blob of chemical B, which is in blue. You've got this big wash of chemical A in red, a bit like the table we saw earlier. So I don't know if you can see this because the contrast isn't great, but you've got this kind of Celtic cross shape slowly evolving on the screen. And they'll keep doing that for a while. It kind of does its own thing. Each one of the, you can't really see the individual cells here, but you can imagine they're in there somewhere. And they're all working on local rules. Remember, they're reacting and then diffusing. And this interesting intricate pattern just comes from that simple process. So now we've seen what it looks like, let's look at the formula. So I don't think this needs explaining, so we'll go on. Oh, okay. You want me to explain it on a term-by-term basis? Okay, fair enough. So this, I will admit, is not my formula, and it's not Turing's formula. It's by a guy called Carl Sims, who has got a fantastic website with much better images and pictures and descriptions than I have. But I'm ripping it off. Hopefully he won't mind. That's the A and B. These are two separate lines for different chemicals. A and B is the previous value, okay? DA and DB are how much each chemical should diffuse. Now you can see here there are no numbers because that's configurable. But the point is that we multiply DA, for example, by this term here, which is the convolution earlier, the diffusion of A. So multiply these two together, and then subtract A times B times B, here, B squared. Now what that is the actual definition of the reaction between chemical A and chemical B. And effectively what it describes is, for one chemical A and two chemical Bs, you get back 3 chemical Bs. Hopefully my maths is correct there. We subtract that from chemical A because it's taking away from chemical A. We then add a feed term. Now this is not a function call. It looks like a function call. It's just brackets. When the symbols are next to each other, you're just multiplying, right? But F here, feed, is just an arbitrary number. That's configurable. You're expected to change that, which is why it's not defined here. But you multiply it by 1 subtract A. And the effect of that is essentially it means that the feeder chemical, chemical A, asymptotically reaches 1. It will never go above 1 because when you remove some of the chemical A when it reacts with chemical B, you then add some more feed chemical, but you'll never add more than 1. So let's say it's 0.9, you would then times that by 1, subtract 0.9, 0.1, multiply it by that, so it never goes above 1. And then you multiply by the time delta, which in this case, for our purposes, we'll just say it's fixed. You don't have to worry about that. Just assume that's 1. Then you've got the same thing for B, okay? So you're taking B, you're adding the diffusion of B with the diffusion rate for B, then you add the reaction. So before with chemical A, you're taking away, now you're adding. It's exactly the same calculation, but you're adding it. And then you subtract feed plus the kill rate, which again is just another constant. I wouldn't read too much into the fact it's feed and kill, but you add them together and then you multiply by B. So as b goes down, the slower, the closer to 0 it gets, the less you're going to subtract. Because if it's 0.1, then you multiply the subtraction by 0, and it gets less. So it never goes below 0. So that's the formula. Let's implement it. So in JavaScript, you do it like this. Let's implement the convolution first. So we've got our weights. We saw those before. This is just an averaging set of convolutional weights. This is just your simple nested for loop going through for y, for x, add up to the sum, all of the weights multiplied by the previous value, and this is just a multi-dimensional matrix. That's pretty much right. So that's just that aspect of the equation. The rest of it is here. So you've got feed at 0.055. Actually, Carl Sim's website recommended these because they work quite well. The original animation of the kind of red and green Celtic cross was based on these parameters. The reaction, really simple, A times B times B. And then, as you can see, these kind of directly correlate. You've got the previous value of A plus 1 times diffuse, so the chemical A diffuses at a constant rate, 1. And then you subtract the reaction, add the feed value multiplied by the inverse of A. And B, hopefully you can see this, diffuses at a slower rate. It diffuses at 0.5 times, so it's half as fast at diffusing as chemical A. You add the reaction, then you subtract the feed plus kill multiplied by B. So yeah, we've implemented it. You'd probably have this drawing to the canvas, put it in a web page, you're done. Walk away. Let's go home. Oh, there's a problem. And the problem is that I tried doing this, and JavaScript is way too slow. Even if you rewrite your JavaScript to be like a C program, you pre-allocate your arrays, you treat it as though you've got this constant amount of memory, it's still way too slow. So what's the solution? Well, if you were paying attention earlier, you'd know that there is something out there that's very good at doing lots of convolutions. Yeah? That's right. Graphics cards. So let's refactor our JavaScript to run on a graphics card instead. It can't be JavaScript anymore. So I'm going to have to explain a little bit about how to do this. We'll be doing something called GPGPU, which stands for General Purpose Computing, on a graphics processing unit. And on a desktop, you'd use something like OpenCL or CUDA. You can probably do that on mobile as well. And it means that those are protocols, languages, and frameworks that make it very easy to do parallel computation on a graphics card in a nice, easy to do way. There's nice tooling. You can simulate it. It's debugging tools. This is the web, so we don't have any of that. Apple are planning to introduce that with something called web shading language and web GPU, but I mean, that'll be a long way off. They're demoing it in Safari, but it won't be usable for a long time. So we're going to have to do it the old school way. And the old school way that you do maybe 10 years ago is you would represent your data as colors, because graphics cards work with colors. They're good at rendering scenes. If you can just translate the data you're working with into colors, you're all good. An RGBA pixel is 4 8-bit numbers. Yeah, so it's 0 to 255. If you're using a high color bandwidth monitoring graphics card, maybe you'd have more space. And there are ways to trick the graphics card into having more accuracy, but we won't go into that. We can't do it on the web particularly easily anyway. So let's represent our chemical concentrations as colored pixels. I'm going to have to very quickly explain how graphics programming works. Essentially, 3D programming is split into 2 stages, the vertex stage and the fragment stage. These are 2 small programs that you provide to the graphics card, and you write it in a simplified, effectively a version of C called GLSL. If you're doing Microsoft development, it'd be HLSL. And the vertex program runs for every single point in the triangle. You can't see any triangles here, but imagine this polygon's made of triangles. The fragment shader runs for every single pixel inside every single triangle. So it's running quite a lot, depending on your resolution. And it's called a fragment shader because there's not a one-to-one mapping between pixels and fragments. If you're using anti-aliasing, for example, there might be 4 fragments to every 1 pixel, and they're averaged to give you a better picture quality. They're called shaders because historically they were used for lighting only, but we're going to be co-opting them to do arbitrary computation. Yeah. Graphics cards can also be instructed to render to 2 different targets. They can render to the screen, so you'd see the monkey head on the screen, or they can render to memory. This is often known as a frame buffer, and given that you're rendering to somewhere in the computer's memory so it can put it on the screen, it would be the screen frame buffer and an off-screen frame buffer. If you represent your data as a 2D grid of colors and iteratively write to an off-screen buffer, you can use a previous off-screen buffer and the data, the model you're putting in and the program you're running to iteratively compute more information. This is obvious from the diagram, really. Red monkey head, add to yellow monkey head, add to blue monkey head, add to light brown monkey head, makes a lovely shaded monkey head, right? Yeah, it's obvious. But then it goes back again, so you use the old frame buffer. It allows you to do huge amounts of calculations at once. In this case, we're simulating a simple 2D grid, so we don't need a complex 3D model. We're just having two triangles stuck together into one rectangle. You can see the individual pixels here. They're blown up. They're massive. So yeah, I'm going to be using an online IDE called Shadertoy. It reduces a lot of the hassle. I could have done this myself, but I didn't have the time, and I thought I wanted to learn Shadertoy. It deliberately forces you to write all of your graphics processing as fragment shaders. There are no way to input complex 3D models, so it's almost like code golf in a way. And it's very easy to share. It's quite fun. Yeah, so this is JavaScript compared to GLSL. I don't know if everyone can see that, but very, very similar here. This is our convolution with JS, for loop, adding things up. In GLSL, I'm using a two-dimensional vector. Basically just means two numbers because we've got chemical A and chemical B. If I was doing it properly in JavaScript, I'd also have two numbers, maybe an array. Adding up the coordinates here, slightly different because it's running on the graphics card. Coordinate system slightly different, doesn't matter. Adding up the weights, exactly the same. Loading it from a texture. This is like a texture read, but we're loading in the previous stored data, which is exactly the same as what we're doing there. So let's see what it looks like. The nice thing about this example is that it's going to show you the exact chemical concentration involved without any post-processing. It also looks most like a puffer fish or a coral. I don't know if this is going to work. We'll see. What happens when I click this? Good. It worked. OK, cool. So this is what you saw before, but now it's running in real time. As you can see, I can click and drag. I can add more chemical B. Whoa. As you can see, it's evolving in front of you. It's undulating in this interesting pattern. Remember that you've seen all of the maths involved in this now. That formula, that simple, I mean, what? It was like 15 lines of code. And most of that was just indentation. So this is doing some really fascinating stuff. You can see it's kind of self-healing as you drag and try and destroy some of the chemicals. It just comes back. And it automatically creates this kind of pufferfish effect. I want to show you very, very quickly how easy. I hit escape, and then nothing happens. So I hope I haven't hit escape on QuickTime. We'll see. So you won't be able to particularly see the code here, but I want to show you that there's, I'm not lying to you, very, very small amounts of code here. You can change the reaction coefficient if you want. We could do something weird, like see what happens if we put in 4 here. Click play. Not a lot. Let's go down to 2. Something's happening. Sort of increasing the density. Again, that's really hard to see, but if you're up close, it'll be easy to see. I'm also going to show you how easy it is to change the colors involved. Some ugly code that I didn't delete here, but just disregard that. So the best way to do it would be something like this. What's your favorite color? An easy one to do in RGB, please. Peach. Oh, that unfortunately doesn't accept CSS names. So let's make it something like, let's mix between, let's go with a lovely, bright, sickly green. So this is a VEC4. You can't see this because it's absolutely tiny, but I'm not going to make it bigger. And then let's mix between that and maybe like a bright yellow. Sorry? Oh, red. OK, let's go with a red. It's always fascinating watching people type, isn't it? Yeah, it'll work first time. It should. You've got eagle eyesight. There we go. Get you in a fighter jet. Don't know why I said that. Oh, it's green. Wow. Now, the reason why there's not much red is because there's not much chemical B. So if we did something like, I don't know, divide by 0.1, the nice thing about fragments is you have to think very kind of viscerally. Oh, there we go, we've gone too far, so let's try and go like this. Well, that was the other way. Let's go with 1.5. You can kind of see a little bit of green. Let's make it a lovely yellow. Ah, there you go. Can you see that? So now you can see how easy it is to make garish, ugly things. It does require a bit of messing around. So that's the first simple demo. So again, here's the code involved. I'm putting this here so you can contrast and compare to the next couple of demos. So let's see what the next one looks like. I'm going to move my thing over here. Oh, that did not actually link up. Oh, that's too far. OK. There we go. Zebra. So let's see if we can simulate a zebra. Now, the interesting thing here, I've changed a few things, because sometimes you need to do a lot of fiddling around with the maths. But the main interesting thing is I've changed my weights. I've now got 2 sets of weights. And you can see that they're asymmetric. Okay? So on the right, there's 0.3. On the left, 0.1. So we'll see what happens there. This one's the inverse. And in this bit here, which you might be able to see, I'm basically adding up the weights. But I'm using a function called mix, which in GLSL basically picks between, linearly interpolates between first 2 arguments based on the third. So this has to be a float between 0.0 and 1. So I'm saying mix between 0.5 of the left weight and 0. Oh, no, that's not true. I'm mixing between the left weight and the right weight based on the UV coordinates. Just imagine that's the dimensions of the x-axis. So it's going to pick either side. And actually, I'm not mixing. I'm stepping between 0 and 1. And then after that, in the y-axis, I'm mixing between that and a weight of effectively 0. You might not be able to predict what will happen, but let's see if this looks a bit like a zebra. Now, it's going to take a little while, so I'm just going to click and drag and get it going. So again, exactly the same rules. A bit of fiddling around with some of the coefficients. And the main effect here is the weights, the consequence of picking between those 2 weights. I think this looks like a zebra, personally. Never seen one in real life, but if... yeah, and as we see it evolve over time.
Does it follow a perfectly straight line right down to it?
Well, that's because I'm picking between the 2 weights. I was kind of hoping that wouldn't be obvious. It sounds it sounds arbitrary, but I mean this is all arbitrary, so it's fine. The point is that I'm not putting in a rule called make it like a zebra. I'm putting in some very simple rules that emergently, my worst crime is having 2 sets of weights that I arbitrarily pick between. Exactly, and that is how zebras are made. So there you go. You've seen that on zebras before. It's just like a zebra. And look, you can mess around with the zebra. Oh, stop it saying I'm adding more chemicals to the zebra. Yeah, I have been warned for that. Okay, so let's move on. I'm going to have to go out of this again. So go back here. Sorry, I'm having to exit out of Shadertoy's full screen mode, and it's a little bit janky. Good. Now, you might be thinking, what if you're running all these Turing patterns at once? Well, Shadertoy is using the request animation frame function that the browser exposes. So the moment the tab's hidden, it stops doing any work. That also means that you have to run it at 60 frames a second. So if you wanted to run the simulation faster, you're out of luck. You'd need to build it yourself then. You could drive the graphics card as hard as you like. It's just messing around. It's just a toy. So next one. This is my favorite. I call this one brains. Now this is exactly the same rules as before, actually. So we've gone back to the original weights. But the interesting thing is when I'm rendering this to the screen, I'm doing a bit more interesting, shiny stuff. I'm actually using a convolution that does edge detection here. Okay? So you can see that there's an asymmetric corner here, 1, 1, 1, 1, 5, minus 2, and it kind of all adds up. We'll see what happens. I'm also cheating a little bit. Shadertoy makes it easy to add textures in. And I'm mixing some textures in just to give it a bit of flavor. So that's not to do with Turing. That's just to do with me. So we'll see what happens. If you're squeamish, look away now. hopefully you guys can see the lighting effect of the edge detection. What do you think? Do you like it? Yeah. Well, you're very welcome. I mean, the link's on here, and it will just run on any connected to your TV. Let's destroy the brain. Oh, it's kind of growing back. Oh, so there you go. That's exactly the same rules that you saw before, but just dressed up in a way that looks gooey and disgusting. So there you go. That's brains. And then you can see, you know, the texturing is extremely subtle. At the back, you won't be able to see it, but without it, it looks just kind of flat and a bit boring. So trust me, it really helps. So we're going to go to the next demo now. So this one I call mitosis. And this is honestly gobsmacking. It's gobsmacking. It's quite hard to say. Because we're changing the rules very slightly. We're introducing a third chemical, because we always have the feeder chemical, chemical B. Now we've got chemical C. And you can see the reaction is exactly the same, okay? So A times B times B, A times C. But now chemical A is subtracted from the reaction term, reaction B plus reaction C, and C is taking on reaction C. What do you think is going to happen? Oh, the other thing I haven't talked about is the fact that I've slightly adjusted the kill rate, the feed rate. The feed rate has been reduced from 0.055 to 0.028. I know those off by heart because I've been looking at them a lot and slightly tweaking them. There's something amazing that happens. You wouldn't need a third chemical to get this effect. The third chemical just makes it even better. But with that feed rate pulled down, something incredible happens. So I click and drag. Hopefully you can see this at the back. Yeah. Same maths, same formula you saw, just with some of the variables slightly tweaked. I mean, the difference between that and the first one you saw, the brains, was, well, the difference between 0.055 and 0.028. That's pretty incredible, right? That's amazing. Don't know what the practical implications are, but it is. It's incredible. They're competing. They're fighting over chemicals. Wow. Okay, so that one's mitosis. And as you can see, I've applied the same lighting effect to make it look kind of more gooey. I've gone with the pink and purple to make it look like, what's that, like gram-negative and gram-positive bacteria. It's a fairly kind of bacterial and organic fixation here. There you go. And again, you can see the code. There's a lot of comments because I was desperately working on this as quickly as I could, but there's actually not a lot to it. Look, I mean, ignoring the comments, very, very simple stuff. Okay, next one. Oh, I've got to go back to the old presentation there. I call this predator/prey. Now, this is based off of mitosis, but I've slightly adjusted the rules. Now, chemical reaction B is the same, A times B times B. Reaction C is really complicated. It took ages to make this work. Stayed up really late to make it work. Chemical A has it been slightly tweaked? It looks pretty similar, actually. The interesting thing is with B, we're now making B diffuse at a slower rate now, okay? Chemical B diffuses at a slower rate. Chemical C diffuses at the same rate that chemical B used to. And you've got this term here, B to C. As you might be thinking, it's transforming chemical B into chemical C. And then there's a slight term here that makes C slowly ebb away over time. This one will blow your minds. It blew my mind. When I saw it, I was like, oh, yes! Can everyone see that at the back? Yeah, thanks, man. That's incredible. Same maths. I've just slightly tweaked some of it and made some slightly arbitrary changes. When I first got this working, it would quickly blow up. Either green would win or red would win, and then they'd all die out. So I have had to tweak it to make it kind of stable. I don't know how long this will go on for. This is like the ultimate screensaver. I could watch this forever, and I plan to. But, yeah, quitting the job. But I don't know how long this will last. I've watched it for maybe 10 minutes before, but Oh no, that makes you sound weird, doesn't it? It's just too long to make you think, what's he really, he's got nothing on. It could last for an hour, 50 hours, 10 years. Would it keep going forever? We don't know. Hopefully, the better green does, the better red does, and vice versa. But yeah, I love this one.
Some more red in that bottom left green.
All right, let's help out the red. My pointer's just alternating between red and green every couple of seconds. There's no easy way to mess around with this stuff. There's keyboard inputs, but I mean, who needs that? By the way, this stuff works on mobile, not particularly well. It runs beautifully. Shadertoy is just awkward. You can't really drag. But there you go. There you go, red's winning now. But then green's sort of taking over again in the middle. I often think it's quite sad. Look at these two, right? They're like, star-crossed lovers, just eating away at the green, and then when they come face to face, oh no, and they die. It's a bit like me and my girlfriend there. Yeah. I don't know what that means, but that's... Right. Okay, moving on very, very quickly. So, you might be thinking, wow, how does this all relate to leopard spots? Well, here's for the finale. Cheetah spots! Yeah, it turns out leopard spots are really hard to do because they're kind of a brown patch with little bits of black splodges. And I'd need like a 3-chemical solution to make that work. I spent ages this lunchtime working on it, just couldn't figure it out. So in the end, I went with cheetahs, which only have little round spots. And to treat you guys, I added some textures and added a bit of colors so it should look a bit nicer. And you can see I'm doing the texture axis here. This is just to prove that I'm honest. This is not, you don't have to understand exactly what's going on here. This is sort of a nice yellowy color. Alan Turing's Cheetah Sports. Imagine if it hadn't worked. What a disappointing finale. And as you can see, actually, this is just a modified mitosis. And it's kind of almost there. You can kind of see that, right? Aside from these big bits, that's more like a giraffe. It's like a half cheetah, half giraffe. Imagine that. Yeah. Yeah, so there you go. That's Alan Turing and the Cheetah Spots. In 6 months' time, I'll get back to you with the leopard spots. There was actually a paper about how to make leopard spots with this stuff, and they had to write a paper on it, so the chances of me doing it at lunchtime is quite low. The beautiful thing about all of this is messing around with the colors is so easy, messing around with the maths, there's really not a lot of code here, so it takes you 20 minutes to come up with something really fun. There's loads of ones on there that I came up with, and I want to show you, but I don't really have time. If you're interested, I'll send you links later. So what's next? Conclusion. Why am I telling you this? So I kind of wanted to make the point that, first of all, you don't need to have a maths degree to have fun with maths. I have no education, but I followed along. And got a C at GCSE Maths. General processing on GPUs is not an arcane science. It's easy, straightforward. This took me an evening to put together and then tweaking and the actual slides, but the code, very straightforward. Procedurally generated art, I want to talk about that. This has a lot of the kind of qualities that you see with procedurally generated art. It has emergent effects. Change a small thing, you get this beautiful thing that you can maybe never capture again if you don't save the exact parameters. This was invented by Turing in 1952. And he didn't even use a computer. That's incredible. What was he thinking? But he was using it just for biology. It's still used now as a model. Actually, that was my 3 points. I wanted to finally say, I'm Will. I work for Iike Tricity. We're a green energy company. We're a dark green energy company. We actually make our own energy as well as just trade it. I make our own green energy. We're based got an office in Bristol. So with these guys at Runway East, we're on the 5th floor. And we're hiring for node devs and for QA, automation QA and manual. But also node devs, anyone who likes AWS or wants to learn AWS, speak to me afterwards. Yeah, that's it.
So you know the game of life?
Yes.
That kind of inspired by this as well?
Yes, I'm really glad you asked that question. You'd almost be a plant, but you're not a plant. So yeah, that's a really good question. So it's very similar to the game of life. And I don't know how many of you guys know about Game of Life, but essentially Conway's Game of Life, it's almost like that, but discrete. you don't have this nice or gooiness, it's just individual digital cells that have these certain rules. If I'm surrounded by some cells that are on, I go dark, or vice versa. And you can produce these amazing, incredible, I mean, you could spend forever researching it. One of the Conway's Game of Life rules, I think it's like Rule 71 or Rule 72, they found was actually Turing complete. So with enough space, enough time, you can encode anything in this Game of Life pattern. There was a paper that came out that proved that Turing patterns can encode that rule in Conway's Game of Life. So you can simulate Game of Life using Turing patterns, which can then simulate any other computer. So given enough graphics cards and enough lunch times, you could compute anything. So yeah, I mean, they're intimately linked. I bet it would be really hard to figure. I mean, how have they figured out how to do that? I don't know.
Do you know how Turing managed to visualize this? Or was it just all maths in his head?
Yeah, that's a really good question. I suspect, I mean, he must have graphed some of it out. The way he talks about this is interesting because it's from a kind of, it's right at the point where computers are just becoming a thing that people can consider. He talks about it, in some ways he talks about it in a way that we wouldn't recognize. He's talking about very, very mathematical formulas. He's very vague on the biological details, almost self-consciously so. But then in other ways, he's talking about it in a way that seems very modern. His description of the reaction diffusion, it's really easy to follow. He's talking about a grid of uniformly placed concentrations of chemicals. Whether he actually was able to compute this, I don't know. I think, so the graph that the image that you saw at the start was, I think, a very, very small number of cells that he computed, and then he made it look a bit rounder after the fact. So it would be, maybe like a 10 by 10 set of cells, as opposed to ours, which was however large the frame buffer of this screen is. There we go. Thank you.